In 2017, a team of geologists at the University of Utah discovered that a 2,000-year-old Roman harbor wall, exposed to crashing waves for 20 centuries, was getting stronger. Not weakening, stronger. Modern marine concrete, by contrast, begins to crumble in 50 years. The Romans built better concrete than we do, and they did it without electricity, without microscopes, and without any theoretical understanding of what they had stumbled onto. The Pantheon in Rome has the largest unreinforced concrete dome ever built. It has stood since 126 AD. It has no rebar, no steel mesh, no modern admixtures. It was poured in a single, continuous operation by Roman builders working from a wooden mold. Every modern concrete dome of comparable size needs steel reinforcement to keep it standing. The Pantheon does not, and nobody could explain why until the past decade. Concrete is, at its simplest, a paste of water and a binder mixed with rocks. Modern Portland cement, the binder used in essentially every building constructed since the 1850s, is made by burning limestone with clay at 1400 degrees Celsius, grinding the result into powder and mixing it with sand and gravel. It hardens by chemical reaction with water within hours. It reaches most of its final strength within a month. And then it begins, slowly, to fail. Cracks let in water. Water reaches the steel reinforcement inside. The steel rusts, expands, and breaks the concrete from within. Roman concrete fails differently, or rather, it does not fail. The Roman writer Pliny the Elder describes the recipe in his Natural History, finished around 77 AD. Mix slaked lime with volcanic ash from the Bay of Naples. Add seawater, cast around chunks of broken stone or brick. Pliny notes that this mixture, when placed in the sea, becomes a single mass impregnable to the waves and every day stronger. For nearly 2,000 years, this was assumed to be Roman exaggeration. The recipe was lost. Engineers who tried to reproduce it in the 18th and 19th centuries got brittle, weak material. Portland cement, invented in 1824 and refined throughout the Victorian era, took over because it was easier to make, faster to set, and stronger in laboratory tests. The Romans, the official story went, had not been doing anything special. They had simply built thicker walls. That story collapsed in 2017. A research team led by Marie Jackson, a geologist at the University of Utah, brought samples of Roman marine concrete to the Advanced Light Source synchrotron at Lawrence Berkeley National Laboratory. They wanted to see, at the microscopic level, what was happening inside concrete that had been submerged in seawater since the time of Augustus. What they found was not stable concrete. It was concrete that was actively rebuilding itself. The seawater, which destroys modern concrete, was reacting with the volcanic ash inside the Roman mix to grow new minerals, specifically a rare crystalline structure called a luminous Tobermorite and another called philipsite. These minerals form long, interlocking plate-like crystals that grow into and bridge across hairline cracks. Every storm, every tide, every drop of seawater that penetrated the surface was making the concrete stronger by triggering more crystal growth. The Romans, of course, knew none of this. They knew that volcanic ash from the area around Vesuvius, which they called pulvis Puteolanus, the dust of Puteoli, after the harbor town where it was collected, produced concrete of unusual quality. They had figured this out by trial and error over generations. They built bathhouses, aqueducts, harbor walls, and the Pantheon dome with the same basic recipe. They did not know that the chalcedony and analcime in the ash, reacting with the calcium hydroxide of slaked lime in the presence of seawater chloride, would form long-chain calcium-aluminium silicate hydrates that effectively heal cracks for thousands of years. They just knew it worked. Modern engineers cannot easily replicate this. Volcanic ash with the right composition is not available everywhere. That is why Roman provincial buildings in regions without local pozzolanic ash were less durable, and why the technology faded with the empire. The chemistry only works with seawater and ambient temperatures over years to decades. It produces a structure that is weaker than modern Portland cement when first laid, but stronger after a century, and improving for at least 2,000 years. Why did we lose this? The answer is partly that we did not really lose it. Roman concrete construction declined as the empire fragmented and the supply chains for high-grade pozzolanic ash broke down. Medieval builders worked with the materials available locally: lime mortar, brick, and dressed stone, which is why a Norman castle and a Roman harbour are made of fundamentally different materials. The recipe survived in writing, in Pliny and in Vitruvius, and in the medieval treatise of Faventinus. But the practice did not. By the time engineers wanted to revive it, the local volcanic ash deposits Pliny named had been depleted by centuries of excavation, and nobody understood why the substitution of other ashes did not work. What we lost was not the recipe. It was the supply chain, the institutional knowledge of which volcanic ashes worked, and the patience to wait for results that took decades to manifest. Modern construction values speed. Portland cement reaches most of its strength in 28 days. A concrete pour for a high-rise must be ready to take loads within weeks. Roman marine concrete reaches its full strength after centuries. Nobody is willing to build a building today that will be at its weakest the day it is finished, and only at its strongest in 2226. There is, however, a quiet revival underway. Marine concrete that incorporates fly ash from coal-burning plants or ground-granulated blast furnace slag mimics some of the long-term self-healing properties Marie Jackson observed in the Roman mix. New research projects are deliberately formulating concrete with calcium-rich pozzolanic substitutes that grow stabilizing minerals over years. The aim is not to copy the Roman recipe. It is to copy the principle that a material can be designed to improve with age rather than degrade with it. Whether modern industry will adopt this widely is a question of economics and policy more than chemistry. A concrete that takes a century to reach full strength does not fit the quarterly returns of modern construction. But for some applications, seawalls, nuclear waste containment, coastal infrastructure meant to last centuries, the Roman approach has obvious appeal. The Romans did not build for centuries, they built forever. The Pantheon dome has carried its own weight, without help, for 1,900 years. The harbour at Caesarea Maritima still stands underwater, still hardening every day. We have only just begun to understand the chemistry. The civilization that wrote the recipe down is 2,000 years gone. The concrete it poured is still here and still getting stronger.